So, what are we talking about here? Multi-armed bandits. Why are we talking about bandits? We're supposed to be talking about robots and agents in the real world and machine learning and reinforcement learning. What we have here is that the multi-armed bandit is essentially a theoretical version of a decision-making system, and it has a simpler structure than the more general system, which we're going to be talking about for this entire course. So it's really like a basis for that. So if you remember my my crazy logo that I drew one time when I was bored, and now it'll be my official logo. Watch for years. Of course, I can't find it. It was essentially a form of this, where there is different versions of not version, sorry. There are different ways to understand how you can make a decision. What that means. Sorry, I'm now like fixated on trying to bring up my image, which I can't do when I'm in full screen. All right, that's my version. So, because it has a little bit more of my own thinking inside, so bear with me. But this is the classic one, and this is where this is from. So all these slides, at least in this part, are from the Sutton Bartow book, right? So if you load that book, I've modified them a little bit for clarity and color. He doesn't put color in them at all, which is fine. Which can do whatever he wants. But I put a bit of color in. The classic idea is that what we're trying to do is train an agent, an artificial agent. We're trying to understand a biological agent, a person or an animal, as learning in the following way, right? Where the agent has whatever internal memory and models and functions that it has, and it takes some action in the world. It could just be looking, it could be crying, asking for milk, or it could be attacking someone to get their food. It could be a robot moving around. It takes some action, and the world is everything external to the agent that it does not control. And the idea is that's the reality, but this is a black box that contains everything else, right? In most cases, it's going to be the simulator or the video game that we're using. And then that returns you a couple of values. It returns you the next state of the world, so what happened after the action got taken. Maybe your action had no impact. If it didn't, it's still going to say what happens next. So what does the world look like next? And then you're going to get some signal about reward. So how did you do? Either you're dead or not, or you got some food, or you've been punished with an electrical charge. It could be any of those things. And we want this to be an autonomous system where the idea when they were coming up with this was to say something that trains and learns on its own, right? A robot or a system goes around and explores and learns through interacting with an environment, and the environment could be as open as you want. But then it also seems to model the way animals learn in some ways. And so as a metaphor, this is just a very high level scope of what it is. So a couple more words that get thrown in here. Let me see if the next slide. Yeah. So in my version of it, I've still got the rewards, I've got the actions. We're talking about that the model is, the agent is essentially a model. It's a function, it's some kind of box that has a bunch of weights and variables that you're setting in order to come up with, I guess, your belief or your understanding of how the world works and how to take actions, right? And it's always taking inputs about what it thinks is going on and what it should do, right? And so, yeah, I'm saying, our minds are just a very complex function that's constantly optimizing itself by taking input and improving itself, right? You can call that an agent, or you can just call it a model. And then the types of worlds you're in can vary in complexity, but they still have that flavor that they're going to tell you the current state, and then once you do something, you get some feedback about whether it was a good idea or not. But you can't learn about that until you try. You don't just get an example of the data in the first place. Okay, which is how the rest of machine learning and supervised learning kind of works, right? That we give you an example and you try to just learn a function that mimics that. That's not what we're talking about. So why this bandit? So when we say bandit, we're talking about the word comes from like casinos. So this gambling casino. This is a single-armed bandit, right? It's a bandit because it steals your money, right? So you put money in, the things roll around after you turn the arm, and you don't win. Sometimes you win a little bit, but you hardly ever win anything big. Somebody wins big, but it's not you. I guess that's why it's called a bandit. But it's a fun game to pass a little time as long as you're not too attached to winning back your money. Gambling addiction is a serious thing, so we don't want to minimize that. But in reality, you're making a decision when you play that game, right? Like it's the simplest game you could have, which is there's only one button on the controller, turn the arm or not. So you can play or you cannot. So the K-armed bandit problem is slightly more interesting than that, where we say there are a line of bandits, right? So you go into a casino and there's like 100 of these bandit machines, and you can put your dollar into it and pull the arm and not get any money back. And every once in a while you get a little bit of money. But when you're standing in front of that row of 100 bandits, you have a choice. Which one do I pick, right? I pick the one that is most likely to get me money. And that's not an unreasonable thing, because it's not like they are all completely independent and the same, right? The idea that you might get into if you're addicted to gambling that, oh, it hasn't won in a long time, so it's more likely to win now, wouldn't really be true, because there's an equal chance. If it's designed well, these machines, they have an equal chance of winning or not every turn. But some machines might have a higher chance of winning than others. Like they literally could win more often. They're not just fair coins necessarily. So if that's the case, then the K-armed bandit problem is to say, okay, you're making a decision, and you have to choose which arm to pull. And when you pull the arm, you're going to get a reward. Either you're going to lose your money or you'll get a little bit of money from the system. And that's the whole game, right? But you get to play it multiple times, right? So you can play it an infinite number of times, because a mathematical problem, so we're defining as infinite. T is going to be the time step of how many times we've played it. And at every step we play the game, we're going to say, okay, I took an action T, which is I pulled bandit machine 3 or bandit machine 17. A is just going to be which one you picked. And then the reward will be how much money you gained or lost, right? And it'll usually be minus the amount you put into it. Right, and so this is a hard problem because that's all we know, right? So what we're defining here is a value function is our first example of a value function estimate. We're going to see many more versions of this that have more stuff in it, and there's a bunch of things you don't know that make this problem hard, right? We don't know the true value, so we don't know what the reward for every particular machine is, right? So if there's bandit 1, bandit 2, bandit 3, I guess we're going to have 10 because that's what experiments show. You got to pick an action to pick that bandit. And they have an associated reward, right? So each of these guys has a particular reward. And so if you pick that bandit, you're going to get this reward. I'm starting to use this is a notation called influence diagrams. I blanked there for a second. I mean, you want to call them decision diagrams, but decision trees are different. So it's an influence diagram where we have actions being squares, rewards being diamonds, and then eventually you'd have a state as well, which tells you what's going on. So we don't know the distribution of each bandit, so it could be that it just gives you a certain reward, or it gives the more likely thing is that this this reward is actually some random distribution over a value, right? So it could be a Gaussian distribution over some amount of money, and it gives you a chance of winning. And so you don't know the distribution of each of these. And what you want to do is make as much money as possible. You want to play this and increase your odds of winning. In order to do that, you need to try to learn what the values of the different bandits are, basically which ones give out more money more frequently, right? And this part is called exploring. You're trying to explore the space, try out, like if you've never played Bandit 5, down the road you need to play it a few times and get an estimate of like, well, how often does it win, right? Maybe it gives you a little bit of money every 10 pulls. Bandit 2 gives you a little bit of money every 5 pulls. But you also want to maximize how much money you're making as you play, and that's called exploiting, right? So you want to win as much money as possible, but also learn about their distributions as you play. And that's kind of the essential problem. So, so we'll talk about that. The thing that's missing here, which we'll get to more later, is there's no state, right? Meaning these bandits don't have any memory of how often they've been pulled. They're not just waiting in order to give out money every 10 times. They have a probability of giving money at every step, right? Just like flipping a coin. And you don't know the states of their internal mechanisms anyways. So there is no definition of the state of the system here. You're just saying, on average, what's the probability of each of them giving me money? And so what we're trying to do here is define a mathematical kind of language for these types of situations. Okay, so there's okay, so we have a question on the Piazza. I can't pull it over here. Live Q&A, thank you, whoever it was, anonymous. Which is a good question about what's the difference between this and control theory, right? Because you're talking about controlling a system and going back and forth and learning that. So we will get into that more later, but it comes down to this essential thing. I don't have that listed there. You'll notice there's no, the world contains dynamics, right? So, and that's something we've thrown away here in the bandit problem too. There's no state, there's no dynamics, right? We don't know how the machine works, right? And we don't even model it, right? So after it clicks, what happens next, or what its current state is. In reinforcement journaling in general, we are going to have states and dynamics, but we're going to say that the dynamics and this reward are unknown, right? And so in control, you usually know more of those things. We have a formulation for how the dynamics of the world works, and then you try to optimize within that. We say that in reinforcement learning is like just another end of the spectrum, is that some of the things that you know in control theory are not known, and so how would you learn them in a way that's reliable? But they're very tightly related, and actually it's a question even researchers we often talk about and discuss in conferences, because people in control don't necessarily follow that much in RL, and people in RL don't follow that much in control. And we're constantly like, there's a lot of overlap. We should talk about how much there's overlap, but people do some of their own work, but they are very related. But reinforcement learning, the general answer is there's a lot more stuff you don't know, and how would you learn it from experience, given that. So here's some ways we're going to try to learn. So we're going to form estimates, right? So what do we have? QT and Q star. I don't like that the star is on the bottom, not the top. So what we're talking about here is trying to form estimates of the value of taking an action, right? So in this case, we're taking an action, which is to pull one of these arms and just have some probability distribution that comes from it. And we want to estimate capital Q, which is just how we'll represent our value function. We'll have value functions that will be using value functions will usually use capital V or capital Q. And capital V will be like when there's a state, and Q will be in state and an action. So we're using Q here because there's actions. But these are value functions. And really they're estimates of a real number. So why don't we have that? Oh, that's the next slide, okay. We can put that here. There's things I've been meaning to add to the slide that I haven't added. So we could say that Q in this case is, what is N? T. Okay, in this case we're going to say that Q is a function from T A to the reals, right? And T here is just going to be time. So we're going to have something that goes from 0 to infinity, and it's going to be an integer, and A is just going to be the set of actions, right? And so it could be some finite set. For now, we'll say it's finite. It doesn't have to be. In our case, it's the number of bandits, so it could be literally 10 in this case. So we're trying to, because some functions will represent this, so you take an action, it should give you just a number, so how good was that? And once you know this function, so assuming you get this function somehow, you could then decide how to act by forming what we call the greedy action, right? And so this is our first example of a policy. It's policy 1, which is greedy action. You say, if you give me the value function, I'll just take the best action and do it, right? Right, and so this value function, literally in our case, will be if you pick that bandit, right, it's going to be 10 of them. What's your estimated expected value of that? Right, I haven't even shown you the function yet. But it could be something like that. There's going to be some number, right? And then you're just going to pick the one that has the highest value, right? And we're saying argmax because we want to pick the index of the object. We want the action rather than the value itself, right? We're not saying how much would I make if I follow the best action all the time. It's like, which action should I take? Does that make sense? So the reason we want this value Q is so that we can ask it which action's best. And when I said before, exploring and exploiting, essentially, you've got this now, this policy for saying, if I know the value of every action, at least a probability distribution of them, I know which action I should take on average. If you always follow the maximum one, then you're exploiting and just trying to make as much money as possible. If you don't follow that action, then you're exploring, right? And so why wouldn't you follow that action, right? You've got some value function. It tells you an action to take. That's going to be the one that's the best value according to your function. Why wouldn't you take this? Why would the second case ever make sense? Can anybody explain why? To look for something better, yeah. To be locally optimal. Yeah, and we're not even at that point. You're right. I mean, that's definitely going to come up. That you could have you've optimized this thing, and now it's not even a great estimate. But you literally at that point, you don't even know if it's optimal. It just may not be true. Yeah. So when we start at the beginning, we're literally going to assign this randomly. Just fill in the values for Q randomly, and then learn it over time. Right? Because remember, we don't have anything else. We don't have a formula that tells us the probability of anything. We don't have any bias or prior about how likely things are. All we can do is ask the system, pull an arm, see how much we win, and then count how often we win. That's the only access we have to the system. So initially, this queue is going to be very bad, and so you don't want to follow it, right? You want to explore a lot. And a common approach, which we'll see, I think, is to basically randomly explore. Yes, we will. That's the whole point of the next section. Explore a lot with randomization, and then maybe slowly reduce your randomization to use the function once you're more confident that it works. So it's just kind of dilemma of exploration dilemma, which is you need to explore, but you also want to make as much reward as possible. And you have to trade them off. You can flip them across them randomly, but that's going to come up in all of reinforcement learning. But that essential dilemma is more clear here with Multiarmed Bandits because there's nothing else, right? So somebody asked, what do you mean there's no state? So what do I mean there's no state? Does state make sense to people? I mean, probably. You're engineers. Probably a lot of you have taken control classes. The idea that the system is in some state, that makes sense to everybody, right? Like, if it's a robot, obviously, there's all the joint angles of the entire system. Its power level, its position in the room, and the response values of all its sensors, right? For your software that's tracking user behavior on Facebook, it's your current understanding of all the, I guess it's all the people posting in the system kind of in the last 10 minutes and whether you should show them an ad or not, right? How many users are there? Who are they? That's your state. In a bandit, what's the state? It's sitting there waiting for you to put $1 in it, and then you pull the arm, and it either gives you money or it doesn't. But it's supposed to be a random process, right? So if you're flipping a coin doesn't have a state, right? I mean, it has a position, it has a location, a speed while it's flipping. But the internal part that tells you ahead of time, before you flip it, it's going to be heads or tails, it has no state. There's no relevant information that can tell you whether a head or a tail is more likely before you pick it up to flip it, right? So when we talk about state, that's what we're talking about, something that's relevant to the outputs of the system after you take an action. And like for a robot, it's actually relevant, where it is and its power level and all these things. But for a bandit, there's nothing that's relevant because it has a probability of winning every time you pull the arm. And that doesn't change, right? We're saying the distribution is constant, and you don't know anything about it. Now, mechanically, physically, an actual bandit in Las Vegas has gears and a computer inside, so it has a state and all that. But mathematically, we say that doesn't matter because it's just some random distribution. It's no different than flipping a coin, and that's what we're treating it as. Great. So the action value methods, these are methods that learn action value estimates and don't try to do anything. So they're not trying to take actions. You're just trying to learn this function Q, and then someone else will use the Q for something useful. And so like I said, a simple way to do this in a way that kind of ties into a lot of other more complex methods is just to take some observations and come up with a ratio, which you could treat as a probability, right? So, well, in this case, right, no, sorry, it's different. Because the probability is the probability of it producing some action, right? So at this point, we don't have a state, we don't even have dynamics, so we don't know that. We could do, if we just treated this as like not R, so R is the reward that you're getting, right? So literally money from our, if it's our Vegas bandit point of view thing. So what are we doing here? We're weighting the actual value we get, right? So if it gives us $5, we put $5. If we lose, if it gives us nothing, we put -$1 because that's how much the machine costs to play. And we're going to count that it happened, right? If we just put a count here saying 1 or 0, whether you won or lost, then we could compute a probability of winning something, right? That would be more of a probability. But here we're taking the actual value. So it's more like if you're doing the, if you looked at the probability, in the probability stuff, when you talk about the expected value, oh, we had an expected value in a previous slide, right? Or the expectation. Sorry for my messy writing. I should try to make it neater. Yes, on a previous slide we had it, and I didn't even mention it. So here I explained everything except E, right? So E is expectation, right? So we're saying what's the expected value of the reward we would get over time of following actions according to some policy, or whatever actions we did actually take, right? And do you remember how expectation works? What's the core thing of expectation? Somebody, any idea? You're combining two things. The likely value to come out, yeah, so in this case we're going to have the RT, right? We're combining it over time, so we're summing that R, and what do we multiply it by if it's been an expectation? The probability, right? And so the probability of getting reward RT given we took some action AT. Now it's kind of weird in this case because usually you would be like, okay, given that we took an action and we were in state T and we took action T, we got this reward. That's a probability that makes sense because the system has a state, you took an action, and now you get an output, and it's at dynamics, right? But we're actually at a simpler version here where we just say, you took the action. It has no state because it's always the same. It's like a coin. I have a series of coins with different weights on them or something. So that's that probability. So that's why it's an expectation. In the part here, when we're adding it up, we just put 1. We're kind of estimating, we're creating the probability by doing this count, right? Because this notation's weird, right? There's like an indicator function. I don't know if I had that in the slides. So people know what that means. When we talk about an indicator function, it's, we'll put it in bold, I guess. There's another more universal way. Sometimes you'll even have it like this. I like doing it this way. You put kind of a calligraphy I, and then have your rule, whatever it is. That's another way to do it. And the idea is it equals 1 when this is true, and 0 otherwise, right? So the function of this thing, right? It's just 1 if condition is true, and 0 otherwise. So that's the same here, right? So we say the action that we took, why do we have to do it this way? It's because mathematically you have to like combine over all time steps, and you're taking the action that you took at time t. If it matches a particular action, then you did it. So it's probability 1 because it actually occurred. We're not doing, here we're not talking about a probability distribution that we're sampling from, because we don't have a probability distribution that we don't know, right? We pull the arm and it gives us the value. So when we're doing observations, it's probability 1, right? We know what we did, so it's only either 0 or 1, and we count all the rewards we won, and then this is just another way of saying n, right? Because it just means all the actions you actually took at each time step. So you should look at these in kind of this notation, and these things maybe should make sense. If it doesn't, you can kind of keep staring at it or ask people and maybe write out an example. But the simple way of thinking is that, you know, you're playing these machines, and then you track basically how much money you win and keep track of how many times you pulled and say, okay, I won, you know, $27 and I pulled the arms 100 times, and so my value is, you know, 27% on this one. And that's for each machine, right? When A was taken prior in that state, and A is each particular machine. So maybe it'll make more sense once we have a more concrete example of the distributions. So some calculus, we're going to say that if you take enough samples, as you go to infinity, you're going to get an accurate estimate, since they don't change. So that's another thing we can get from probability and the law of large numbers, that as long as these distributions don't change, and we get an infinite number of samples, then eventually we're going to get an accurate estimate, right? That's just true in general. If they change, all bets are off, and you hope for the best, or you find good ways to do it. You know, there's always ways. But it's true because we're saying in this very simple case, nothing's changing. Let me try moving things this way. You can see everything at once. Yeah, and somebody's asking about the reward distribution. So yeah, the reward doesn't change in time steps in this current model we're talking about. But the capital R with a T is the actual reward you received, right? It's not necessarily even a function. It's just a concrete value. How much money did you get when you played it? Okay, so we've got that one.